కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో ఆటోనమస్ కాబోతోంది. 2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning. Okay, in the last classes we discussed about the autocorrelation, cross correlation, relation between autocorrelation and cross correlation functions, and properties of correlation functions. Then energy density spectrum, power density spectrum, and Parsel's theorem, etc. Now we are going to discuss about the detection of periodic signals in the presence of noise by correlation. Detection of periodic signals. How to detect the periodic signals in the presence of noise by correlation. So using correlation, we can detect the periodic signals in the presence of noise. Okay. Using correlation, we can detect the periodic signals in the presence of noise. Okay. Right. So correlation technique provides a powerful tool in the solution of the above problem. So this correlation technique is used to detect the periodic signals in the presence of noise. So we should consider the application of both autocorrelation and cross correlation in the detection of a periodic signal in the presence of noise. Okay. In the presence of noise only we can detect the periodic signal by using either autocorrelation function or cross correlation function. So the noise signal in fact is which is a signal with random amplitude variation. So noise signal means it does not have a fixed amplitude or which does not have a fixed time period, which has a random amplitude as well as time period variations. Okay. If S of t is a periodic signal and N of t is the noise signal. Let us consider S of t. S of t is a periodic signal and N of t is noise signal. Okay. S of t is periodic signal and N of t is noise signal. Okay. Right. So then limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 S of t into N of t minus tau dt is equal to 0 for all tau. What is this equation? This equation is nothing but a correlation equation. Correlation equation, that is integral minus t by 2 to plus t by 2 S of t into N of t minus tau d tau, which is equal to 0. Here S of t is periodic signal and N of t is noise signal. Okay. Next, if we denote del Sn of tau as the cross correlation function of S of t and N of t. What is S of t? S of t is periodic signal. What is N of t? N of t is noise signal. So cross correlation of these two things, S of t and N of t, is nothing but del Sn of tau. Del Sn of tau. That is integral minus integration equal to S of t into N of t minus tau dt. This is equal to 0. This means that del Sn of tau is equal to 0. Okay. So this is what del Sn of tau is equal to 0. Del Sn of tau is equal to 0. Del Sn of tau is equal to 0. Right? Del Sn of tau is equal to 0. Next, detection by autocorrelation. So this is nothing but cross correlation. Next we see the detection by autocorrelation. Detection by autocorrelation.
So if you denote Sn of tau as the cross correlation function of S of t and n of t, then Sn of tau is equal to 0. Why? Because see here in the previous one, here limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 S of t into n of t minus tau d tau is equal to 0 for all tau. This means this is Sn of tau, Sn of tau. Okay, right. So similarly we can detect the autocorrelation. So let S of t be a periodic signal mixed with a noise signal. Okay, that is n of t. Then the received signal is f of t, which is denoted by periodic signal mixed with noise signal. Here S of t is periodic signal and n of t is noise signal. Okay, S of t is the periodic signal and n of t is the noise signal. So let J-FF of tau, J-SS of tau and J-NN of tau denotes these are the autocorrelation functions. So as we already know, the definition of autocorrelation function is the comparison of signal with itself only. See, the comparison of signal with itself only. So suppose if J11 of tau, if you take J11 of tau, means here the signal x1 of t is compared with itself only. That's why it is denoted by J11 of tau. Here also let Jff of tau. So here f of t is a function which is compared with itself only. That is in autocorrelation it is denoted by Jff of tau. Jss of tau and Jnn of tau denotes autocorrelation functions of f of t, s of t and n of t respectively. Okay, suppose if you take Jff of tau, so Jff of tau is equal to limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 f of t into f of t minus tau dt. Right? What is f of t? F of t is nothing but s of t mixed with n of t. S of t is the periodic signal, n of t is the noise signal. So f of t is nothing but combination of s of t and n of t, that is s of t plus n of t. So in this expression replace f of t by s of t plus n of t. Okay, so it is equal to limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 s of t plus n of t, right? In the same manner, f of t minus tau becomes s of t minus tau plus n of t minus tau into dt. Okay, so by multiplying this expression with this expression, it will become s of t into s of t minus tau dt. Okay, plus s of t into n of t minus tau dt plus n of t into s of t minus tau dt plus n of t into n of t minus tau dt. So on the whole it will become Jss of tau, that is nothing but integral minus t by 2 to plus t by 2 s of t into s of t minus tau dt. Okay, next Jnn of tau, that is nothing but integral minus t by 2 to plus t by 2 n of t into n of t minus tau dt. Okay, plus Jsn of tau. Jsn of tau means s of t into n of t minus tau dt. Next Jns of tau means n of t into s of t minus tau dt. So since the periodic signal s of t and noise signal n of t are uncorrelated, so Jsn of tau is equal to Jns of tau is equal to 0. These two are uncorrelated. Jsn of tau is equal to Jns of tau is equal to 0. So in the above expression, Jsn of tau and Jns of tau both are equal to 0. Okay, then this expression becomes Jff of tau is equal to Jss of tau plus Jnn of tau. Here Jss of tau is a periodic signal and Jnn of tau is a non-periodic signal. Jnn of tau is a non-periodic signal, right? The autocorrelation function of a periodic signal masked by noise is as shown like this. This is the autocorrelation function of a periodic signal which is masked by noise. Okay, which is masked by noise. See here, see the dark line waveform is nothing but JFF of tau, and this dotted line waveform is JNN of tau, and JSS of tau is nothing but it is a dotted sinusoidal signal. Dotted sinusoidal signal. Here JSS of tau is a periodic signal and JNN of tau is a noise signal. Okay, so here the periodic signal is masked with noise. So finally the resultant function JFF of tau is represented as this sinusoidal waveform like this. Okay, this is the autocorrelation function of a periodic signal masked by noise. Okay, autocorrelation function of a periodic signal masked by noise. Okay, so in detection by autocorrelation, what we have done here, so let S of t be a periodic signal which is mixed with noise signal N of t. So the resultant is taken as the received signal f of t as S of t plus N of t. So here let us we are considering JFF of tau, JSS of tau and JNN of tau. These are the autocorrelation functions of the f of t, s of t and n of t respectively. So first of all, JFF of tau is represented as integral minus infinite or minus t by 2 to plus t by 2 f of t into f of t minus tau d tau. But f of t is nothing but it is a combination of f of t and n of t. So replace f of t by s of t and s of t plus n of t. Similarly, f of t minus tau will become s of t minus tau plus n of t minus tau. By multiplying these two functions, we will get the resultant function as JSS of tau plus JNN of tau plus JSN of tau plus JNS of tau. Okay, so here JSN of tau and JNS of tau both are uncorrelated, so both are equal to 0. So this expression becomes JFF of tau is equal to JSS of tau plus JNN of tau. So here JSS of tau is a periodic signal and JNN of tau is a non-periodic signal. Okay, so the autocorrelation function JFF of tau can be represented diagrammatically like this. So it is the combination of JSS of tau and JNN of tau. Here JSS of tau is a periodic signal which is masked by a noise signal JNN of tau. So the resultant is JFF of tau, which is represented like this. Next, detection by cross correlation. Here also we are considering the resultant or received signal f of t as the combination of s of t and n of t, where s of t is a periodic signal and n of t is a noise signal. Okay, so here we are detecting the cross correlation function. So JFC of tau is equal to limit tends to infinity 1 by t into integral minus t by 2 to plus t by 2 f of t into c of t minus tau dt. But f of t is combination of s of t plus n of t. So this f of t is replaced by s of t plus n of t. Okay, so s of t plus n of t into c of t minus tau. So multiplying this with this, that is s of t into c of t minus tau dt plus n of t into c of t c minus tau c of t minus tau dt. Okay, s of t into c of t minus tau dt is nothing but jsc of tau, and n of t into c of t minus tau is nothing but jnc of tau. Here c of t is a periodic function and is uncorrelated with random noise signal n of t. Hence jnc of tau is equal to 0. Then it will become jfc of tau is equal to jsc of tau. Here s of t and c of t are signals of same frequency and it follows that JSC of tau is also a periodic function of the same frequency. That's why these two are equal. JFC of tau is equal to JSC of tau. JFC of tau is equal to JSC of tau. Okay, so it is evident that if the cross correlation of the contaminated signal f of t with c of t yields a periodic signal f of t must contain a periodic component of the same frequency as that of c of t, that is jfc of tau is equal to jsc of tau. Jfc of tau is equal to jsc of tau. Okay, so this is the detection by cross correlation. Next we will discuss about the extraction of a signal from noise by filtering. In the earlier topic we discussed about the detection of correlation in the presence of noise, detection of periodic signal in the presence of noise by correlation, whether it is cross correlation or autocorrelation. Using cross correlation or autocorrelation we can detect a periodic signal in the presence of noise. Okay, so in both cases, in cross correlation, using cross correlation and autocorrelation, we can detect the periodic signal in the presence of noise. So that is the periodic signal masked with noise. Okay, next we are going to discuss about the extraction of a signal, how to extract the signal from noise using filtering, by filtering. So by using filtering, we can extract the signal, whether it is a periodic signal or non-periodic signal. So we can extract a signal from noise. Okay, a signal masked by noise can be detected by correlation technique or by filtering. Okay, so suppose a signal is masked by noise, which can be detected by using cross correlation or autocorrelation function. So, and another way of detecting this periodic signal which is masked by noise is filtering. Okay, filtering. These two techniques are equivalent. Here the correlation technique as well as filtering technique, these two are equivalent. So correlation technique means, it means it is means of extraction of a given signal in the time domain, whereas filtering is exactly same result in the frequency domain. That is the only difference. Okay, so it is nothing but in both cases, so the resultant is the extraction of a given signal. Extraction of a given signal in time domain means that is correlation technique. In frequency domain means that is filtering technique. Okay, so in both cases our aim is to extract a given signal. Okay, suppose which is in time domain, then that is called correlation technique, which is in frequency domain, that is called filtering technique. Okay, so now we will see the relation between correlation and filtering. Correlation and filtering. We'll see the relation between correlation and filtering. See, consider two arbitrary signals f1 of t and f2 of t, f1 of t and f2 of t. So the cross correlation function j12 of tau is defined as, see here, suppose if you take the Fourier transform of f1 of t is f1 of w, f1 of omega, and Fourier transform of f2 of t is f2 of omega, then j12 of tau is nothing but the Fourier transform j12 of tau. J12 of tau is nothing but correlation, cross correlation of f1 of t and f2 of t. That is nothing but the Fourier transform of j12 of tau is equal to f1 of omega into f2 of minus omega. Okay, so there is a relation between cross correlation and Fourier transform. So what is that Fourier transform and cross correlation? So these two are equivalent. These two are equivalent if one of the function becomes an even function. These two are equivalent if one of the function becomes an even function. Okay, that's why it will become in frequency domain as f1 of omega into f2 of minus omega, f2 of omega into f1 of omega into f2 of minus omega. So Fourier transform of cross correlation of f1 of t and f2 of t is equal to f1 of omega multiplied by f2 of minus omega. Okay. So cross correlation in time domain and frequency domain are as follows. So here this is the cross correlation in figure A. The cross correlation function f1 of t is cross correlated with f2 of t. It yields j12 of tau. In figure B, f1 of t, the Fourier transform of f1 of t is f1 of omega, which is multiplied with f2 of minus omega, then it will become j12 of tau. Okay, j12 of tau is nothing but f1 of omega into f2 of minus omega. So the impulse response h of t of a system with a transfer function f2 of minus omega is given by h of t, that is h of t equal to inverse Fourier transform of f2 of minus omega. But f2 of t, Fourier transform of f2 of t is nothing but f2 of omega, and Fourier transform of f2 of minus t is nothing but f2 of minus omega, and hence h of t is equal to f2 of minus t. Okay, so Fourier transform of f2 of minus t is nothing but f2 of minus omega, or inverse Fourier transform of f2 of minus omega is nothing but f2 of minus t, that is nothing but h of t. So this result can now be applied to the problem of the detection of a periodic signal from a random noise signal. Okay, let S of t and N of t are the periodic component and random noise components respectively. Then the received signal f of t is the combination of the periodic signal and noise signal N of t. Here S of t is the periodic signal and N of t is the noise signal. The periodic component S of t present in f of t can be detected by cross-correlating f of t with another periodic signal c of t of the same period as that of S of t. Okay, f of t, the periodic component S of t present in f of t, how can be it detected? So it can be detected by cross-correlating f of t with another periodic signal c of t, which is having same period as that of S of t. Okay, so we need a system which has unit impulse response c of minus t, or which has a transfer function c of minus omega, where the Fourier transform of c of t is c of omega and Fourier transform of c of minus t is c of minus omega. Here c of t is a periodic signal of period t naught. C of omega is the Fourier transform of c of t, uh, will consist of impulses located at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught. Okay, plus or minus 3 omega naught up to plus or minus n omega naught, where omega naught is 2 pi by t naught or 2 pi f. These impulses have magnitudes equal to 2 pi times the corresponding quotients of the exponential Fourier series for c of minus t. Thus, if c of t is expanded by Fourier series, then c of t can be expanded in Fourier series as sigma n equal to minus infinity to infinity plus infinity cn into e power jn omega naught t, where omega naught is 2 pi f or 2 pi by t naught. Then Fourier transform c omega of c of t is given by c omega equal to 2 pi into sigma n cn into delta of omega minus n omega naught. Since c of minus omega is equal to c star of omega, then c of minus omega equal to 2 pi times sigma n Cn star into delta of omega minus n omega naught. Thus, C of minus omega consists of impulses located at omega equal to 0 plus or minus omega naught plus or minus 2 omega naught plus or minus 3 omega naught, etc. So, C of minus omega represents a system which attenuates all of the frequencies except omega equal to 0 plus or minus omega naught plus or minus 2 omega naught plus or minus 3 omega naught up to plus or minus n omega naught, etc. So C of minus omega represents a system which attenuates all of the frequencies except 0 plus or minus omega naught plus or minus 2 omega naught plus or minus 3 omega naught up to plus or minus n omega naught. So let us consider C of t to be a sinusoidal signal cos omega naught, and let the cross correlation be performed over a finite interval. Then finite interval minus t to 0, which is as shown as, see here, C of t is a periodic signal, so it is a located between the finite interval minus t to 0, that is the figure A. And if you take C of minus t, that is nothing but it is the mirror image of C of t, which is located from 0 to plus t. Okay. Now you will see the C of minus omega, that is nothing but the transformation of C of minus t. So that is like this. It is varying from minus omega naught to plus omega naught. Okay. So this is the spectrum, Fourier transformation or Fourier transform or transformation of C of minus t. So the Fourier transform of C of minus t is a sampling function shifted by plus or minus omega naught. So figure C is this is nothing but a magnitude spectrum. This is called magnitude spectrum. Okay. So here we are taking the C of t as a sinusoidal signal cos omega naught. Okay. So that is represented like this. So its mirror image is C of minus t, and its transformation or magnitude function is like this. It is a sampling function, which is a sampling function shifted by plus or minus omega naught. Okay. So it is a magnitude function or magnitude spectrum, magnitude function or magnitude spectrum. Okay. So this is about the detection of periodic signal from noise by filtering. Okay. Noise by filtering. So these two topics are over today. Okay. In the next class we'll discuss about the remaining topics. Okay. Thank you.